In our previous video, we've shown problems in traditional definition of knowledge. A possible solution has also been offered by redefining knowledge as adequately justified information. Now we will show how the knowledge is accumulated. The Gettier problem reminds us that a definition of knowledge cannot and should not require complete certainty. Although any account of knowledge that does not bind truth and justification together may encounter Gettier-style counterexamples, this may be an inescapable problem. We shouldn't turn to radical skepticism and claim that we know nothing. Instead, consider the ways we use knowledge in our daily lives. Knowledge serves an important evolutionary function, whether it's the location of a beehive on a mountain trail or that there's a measles outbreak in Philadelphia. Therefore, we need a reliable process for deciding when to trust our senses and others' testimony, even if this process does not result in a foolproof analysis every time. All genuine problems are at least theoretically capable of being solved, said the positivist philosopher A.J. Ayer in 1936. But most philosophical problems, he thought, were pseudo-problems, to be dissolved by close examination of the language in which they were couched. Such a metaphysical pseudo-proposition as the absolute enters into, but is itself incapable of, evolution and progress, he thought, had no literal significance, even for the person who uttered it, because it could not possibly be verified by observation or experiment. Ayer said he plucked that sentence about the absolute randomly from the writings of one of the most typical and dominant late 19th century British philosophers, F. H. Bradley. He was asserting that almost all previous philosophy was literally nonsense, like all mimsy were the Borogoves but less amusing. And Ayer was saying that, if philosophy was to have any respectable, useful or well-defined subject matter, it would be found in the nature and function of language, not the nature and function of reality. This proposition I exist is held true not based on a deduction or on empirical induction but on the clarity and self-evidence of the proposition. Descartes does not use this first certainty, the cogito, as a foundation upon which to build further knowledge, rather, it is the firm ground upon which he can stand as he works to discover further truths. It's unfortunate that he didn't do just that. What could have stopped him from doing it? He could have prevented philosophy from being led astray by subsequent philosophers who came after him. The existence of a conscious entity while thinking is the first knowledge and is the only self-evident information. Its existence in the past and the future are not self-evident, thus require more justifications. Justification for a new information needs to be more reliable than the new information itself. Hence any other information need to be justified by ultimately relating it to the first knowledge through chains of reasonings. Since every other information is not guaranteed to be true, it means that there is a possibility, however slightly, that it will turn out to be false. However, not all information has the same probability to be false. The justifications are needed to accept that a piece of information has higher probability to be true than previously thought. A commonly used method to deal with uncertainty and incomplete information is Bayesian reasoning. Bayesian reasoning is an application of probability theory to inductive reasoning and abductive reasoning. It relies on an interpretation of probabilities as expressions of an agent's uncertainty about the world, rather than as concerning some notion of objective chance in the world. Google Bard says that Bayesian reasoning is a method of statistical inference that uses Bayes' theorem to update the probability of a hypothesis as more evidence or information becomes available. Bayesian inference derives the posterior probability as a consequence of two antecedents, a prior probability and a likelihood function derived from a statistical model for the observed data. Bayesian inference computes the posterior probability according to Bayes' theorem. Probability of hypothesis, given evidence, equals to probability of evidence, given hypothesis, times probability of hypothesis, divided by probability of evidence. Ph vertical bar E, the posterior probability, is the probability of H given E, i.e., after E is observed. This is what we want to know, the probability of a hypothesis given the observed evidence. P vertical bar h is the probability of observing E given h and is called the likelihood. As a function of V with h fixed, it indicates the compatibility of the evidence with the given hypothesis. The likelihood function is a function of the evidence, E, while the posterior probability is a function of the hypothesis. Ph, the prior probability, is the estimate of the probability of the hypothesis H before the data E, the current evidence, is observed. P is sometimes termed the marginal likelihood or model evidence. This factor is the same for all possible hypotheses being considered, and hence does not factor into determining the relative probabilities of different hypotheses. A geometric visualization of Bayes' theorem. In the table, the values 2, 3, 6 and 9 give the relative weights of each corresponding condition and case. The figures denote the cells of the table involved in each metric, the probability being the fraction of each figure that is shaded. Probability for someone to have astigmatic, after we know that he has beard, equals to probability of people having beard among those with astigmatic, times probability of people to have astigmatic, divided by probability of people having beard. The results of Bayesian inference are interpreted using a posterior distribution. The posterior distribution is a probability distribution that represents our updated beliefs about the parameters of a model after we have seen the data. The posterior distribution is a combination of our prior beliefs about the parameters, and the likelihood of the data given the parameters. There are a few different ways to interpret the results of Bayesian inference. One way is to look at the mean of the posterior distribution. The mean of the posterior distribution is the most likely value of the parameter. Another way to interpret the results is to look at the credible intervals of the posterior distribution. Credible intervals are ranges of values that are likely to contain the true value of the parameter. The results of Bayesian inference can be interpreted in a number of ways, depending on the specific application. However, some general principles can be applied. Credible intervals. Bayesian inference often produces credible intervals, which are ranges of values that are likely to contain the true value of the parameter being estimated. The width of the credible interval indicates the uncertainty in the estimate. Posterior probabilities. Bayesian inference also produces posterior probabilities, which are the probabilities that different values of the parameter have, given the data. These probabilities can be used to make decisions about the parameter, such as whether to reject a hypothesis. Priors. The prior distribution is a key part of Bayesian inference, as it represents our prior beliefs about the parameter being estimated. The prior can have a significant impact on the posterior distribution, so it is important to choose it carefully. In general, the interpretation of Bayesian inference results should be done in a way that is consistent with the specific application. Bayesian reasoning makes it possible for us to learn new things from new information, without having to completely throw away our current knowledge that we've got from past experiences. That's how we can accumulate knowledge to improve our level of consciousness, which would be instrumental in our effort to pursue the universal terminal goal. Our knowledge can affect our decisions in various degrees, based on their importance. We will discuss about it in the next video.